So this is a track, and these carts roll on the track. They're not motorized, they just have little spinny wheels. And they just roll back and forth, they fit in there, and they roll pretty smoothly. So if I just get it going, it's not much friction. And so I'm going to give you some examples of collisions. And so these carts have, on one side they have magnets, and so they repel each other. And so I'm going to have this cart here collide with this cart, and we'll just watch what happens. They're identical now, they have the same mass. And so I'll send that cart in, and hopefully you see that this cart stopped, and this cart went off with about the same velocity as this guy started with. So I'll do that one more time. Let me get that one stopped. You can kind of see that the momentum is transferred from one cart to the other. Right? This is called an elastic collision because kinetic energy is conserved. We'll talk about that later on. But now I'm going to put a little more mass on one of the carts than the other. These are 500-gram weights. And so now this cart is considerably heavier than this one. You'll see something different will happen. This one shoots off a little faster than this one was coming in, and this one keeps moving forward. So let's try that one more time. So I'm going to send him in like this, and this one clearly runs away quicker, and this guy keeps moving forward. Now I can reverse that, and I can have the lighter cart come in, and you can tell me what you think is going to happen, or at least you can tell yourself what you think is going to happen. I'm going to send this cart in this way, and what you'll see is that it bounces backward, and this guy moves forward slower than this guy came in. So I'll put it over here to give it a little more room. Well, it came off the track that time, so we'll try it one more time. So I'll put this one here, maybe, like that, and I'll send this guy in. This guy creeps on out, and this guy goes backwards. So when the heavier guy is coming in, they both end up going that way. When the lighter guy is coming in, the heavier one goes that way, and the lighter one goes backwards. Those are elastic collisions. So now I'm going to reverse the carts. On the other side of the cart, they have Velcro. There's some Velcro. And so you'll see, whereas, well, let me turn it back the other way. Whereas before when they were colliding, they interact through a magnetic field, and one of them pushes the other one along through the magnetic field. Now when I turn them around like this, they'll stick. They got Velcro on them. And so we're going to see what happens then. And so I'll start, first of all, I'll start like I did before with two cars that have the same mass. And now they stick, and hopefully you see that they go slower. Right, when I send one in at a certain velocity, the two go off together at a slower velocity. Right? Similar when I add mass, if I add mass to this guy, finally I can add mass to this guy. When the big guy comes in with momentum, they still carry away a good bit of velocity. When the little guy comes in, they carry away less. So we'll be analyzing these collisions as we look at conservation of momentum problems. I've given you the first set I did was elastic. These are called inelastic because kinetic energy is lost in these collisions where they stick together. Technically, they're called perfectly inelastic collisions, but it doesn't matter too much. So we're going to talk about conservation of momentum here, and we're going to say we're going to look at it in the context of a collision. So we just looked at a collision between the two carts on the track, and so I'm kind of trying to draw those here. These are carts that are free to move in sort of one direction on a track, right? This is cart M1, this is cart M2. I'm just speaking about them kind of generally. Then we're going to say before they've collided, this guy has V1 initial velocity V1. This guy has V2 initial. We can assume he's at rest, but he doesn't have to be. He's just got to be going slower than this one guy is, so they collide, right? And so I can say, look, this guy's momentum before the collision is just his mass times his velocity, so P1 initial is equal to M1 V1 initial. Similarly, this guy's initial momentum, cart 2's initial momentum, if it's traveling at V2 initial, is P2 initial is equal to M2 V2 initial. Then there's a collision, right? They collide, and now this guy is going at V1 final, some different velocity after they've collided. maybe is at rest. And so P1 final is equal to M1 times V1 final. Similarly, the final momentum for cart 2 is equal to M2 V2 final. And so we're going to try to draw conservation momentum out of this. And so, P tote initial is equal to P1 initial plus P2 initial, right? And similarly, P tote, the total momentum finally, is equal to P1 final plus P2 final. I'm going to get a better marker. So now we can say, well, what happens? How does the momentum of cart 1 change? So So the change in momentum for cart 1 is equal to the force that it experiences. That is the force due to cart 2 on cart 1. When they collide, cart 2 exerts a backward force on cart 1 times the collision time, right? This is the impulse equation. And so I can say delta P2 is equal to P1 final minus P1 initial, or P1 final is equal to P1 initial plus delta P1. In other words, this change in momentum, the change in momentum this cart experiences from here, between here and here, is the force that acts on it times the time. That's what its change in momentum is. And so its final momentum is related to its initial momentum by adding delta P1. Similarly, I could say cart 2 gets acted on by cart 1. Delta P2, the change in momentum for this cart, is F1 on 2 times delta T. The change in momentum for cart 2 is the force that acts on it times the time, and that's due to the force due to cart 1 on cart 2. And so, similarly, P2 final is equal to P2 initial plus delta P2. Now here's the thing. I'm going to have to erase this over here for a second. According to Newton's third law, the action-reaction law, these two are equal and opposite forces. So F2 on 1 is equal and opposite to F1 on 2. And so delta P1 is equal to F2 on 1 times delta T, right? And that's equal to minus F1 on 2 times delta T, which is minus delta P2, because delta P2 is F1 on 2 delta T. So, if delta P1 is the same thing as minus delta P2, then I can say, look, P1 final plus P2 final is equal to, I'm just going to take this guy and this guy, is equal to P1 initial plus delta P1 plus P2 initial plus delta P2. Right? If I take this definition for P1 final and this definition for P2 final, put the delta P's in there, but notice delta P1 is equal to minus delta P2, so these guys add up to 0, and so I get P1 final plus P2 final is equal to P1 initial plus P2 initial. This says the total initial momentum equals the total final momentum, conservation of momentum. again, the system has to be isolated. These guys can only act on each other. I can't have other forces going in there acting on while this is going on. But as long as the forces are between these two guys, it doesn't matter, because however much momentum this guy loses, this guy gains in that process. And so when you add them up at the beginning and at the end, they add up to the same thing, conservation momentum. So Mary has a mass of 60 kilogram, and she ice skates at 8 meters per second towards Bob, who has a mass of 90 kilograms, who is skating away from her at 2 meters per second. Mary jumps on Bob's back, and they skate off together. What is their final velocity? And so here's I guess I have to put little skates on them, right? There's Mary. She's going V1 initial is 8 meters per second. Here's Bob. For some reason, Bob has a larger head. They're wearing hats. Smiling. So this is V2 initial equals 2 meters per second. And then we're going to say, so after she jumps on his back, I don't know how I'm going to do this. So I guess I'll draw Bob first. And then Mary's on his back somehow. Right? Okay. So now they're going off together, right? It's frictionless ice. We're going to say for this argument, right? And so we're going to say, look, we're going to use conservation momentum here. We're going to say, look, the initial momentum is equal to the final momentum. That's what we showed on the last slides, right? We showed that the total initial momentum is equal to the total final momentum. And that means P1 initial plus P2 initial is equal to P1 final plus P2 final. Well, what are these? This is M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final, right? And it says, you know, what is their final velocity? Well, they skate off together, and so this is V final here. Right? And so what I get here is V1 final is equal to V2 final, because they're stuck together, and I can just call that V final. And so this equation becomes M1 V1 initial plus M2 V2 initial is equal to M1 V final plus M2 V final. Well, I need to solve this for V final, and so I can, if I want, I can just write this guy as M1 plus M2 times V final, right? And so this gives me, I can say V final is equal to M1 V1 initial plus M2 V2 initial over M1 plus M2. Right? I just divide out the M1 plus M2, and so this is 60 kilograms times 8 meters per second plus 90 kilograms times 2 meters per second, all over 60 kilograms plus 90 kilograms. Well, 60 times 80 is 60 times 8 is this is 480. I'm going to convert it to Newton seconds instead of kilogram meters per second. It's just easier to write. Plus 180 Newton seconds, because that's 90 times 2, over 150 kilograms. 4.4 meters per second. That's their final velocity. It's reasonable. It kind of checks out. It should be between one of those. You wouldn't expect them to be going faster than 8 or slower than 2, right? And so it's somewhere in between there. A little closer to Bob's because he has a little more mass. So here's another conservation of momentum problem. A 100 kilogram man stands on frictionless ice and is shot in a bulletproof vest by a bullet that has a mass of 20 grams and is traveling with a velocity of 600 meters per second from a military rifle. What is his speed after the bullet hits, assuming it sticks in his vest? Again, this is an isolated system, and so I can just say, look, the final momentum of my system is equal to the initial momentum of my system. I've got no external forces. He's on frictionless ice and so on. And so this says, we'll call the bullet M1 and this guy M2. And so we're going to say V1 initial is 600 meters per second, and V2 initial is equal to 0 because he's just standing there. And so I'm going to say P1 final plus P2 final is equal to P1 initial plus P2 initial, right? And his initial momentum, V2 initial equals 0, and so I can just drop that guy, right? Because P2 initial is equal to M2 V2 initial. And since this guy's 0, the product is 0, right? And so the other thing I can recognize is that this is M1 V1 final plus M2 V2 final equals M1 V1 initial, and V1 final equals V2 final equals V final, right? That is to say, once they stick together, then their two velocities are the same. So this one becomes M1 V final plus M2 V final equals M1 V1 initial, or V final is equal to M1 V1 initial over M1 plus M2, and that's 0.02 kilograms times 600 meters per second all over 100.02 kilograms, right? Because it's 100 kilograms plus 0.02. Clearly the 0.02 doesn't matter down here because it's just a tiny fraction of the mass of the man. This is 2 times 10 to the minus 2. This is 6 times 10 to the 2, so this is 12 kilogram meters per second over essentially 100 kilograms. You can keep those extra 2 significant figures if you want. They're not going to do you any good. And so this is equal to 0.12 meters per second. So this is a high-power military rifle, and you can see when it's all done, he's traveling at maybe 4 inches per second. This puts a lie to the the movie scenes where a guy gets shot by a military rifle and he goes through a plate glass window and over a car and lands halfway across the street or something like that. And that's if he had friction, right? Here we don't even have friction. This is the best you're going to do. If you got shot by this thing, you could probably just use friction and not move at all. Your momentum would be incorporated into the momentum of the Earth somehow. So let's do a little more with Bob and Mary. We said Mary had a mass of 60 kilograms and an initial velocity of 8 meters per second. Bob had a mass of 90 kilograms and an initial velocity of 2 meters per second. And then we said their final velocity, V final, which is just V1 final and V2 final also, because she was just hanging on his back, was 4.4 meters per second. And so let's look at the kinetic energy of this system, right? KE1 initial is 1/2 M1 V1 initial squared, right? And that's 1/2 times 60 kilograms times 8 meters per second. squared, which is 1920 joules. Similarly, KE2 initial is 1/2 M2 V2 initial squared, and that's 1/2 times 90 kilograms times 2 meters per second squared, which is 180 joules. Notice since the kinetic energy is proportional to the square of the velocity, right? The person who has a lot more velocity is going to have a lot more kinetic energy because it goes as the square of the kinetic energy is proportional to the square of the velocity, right? And then we can calculate the final kinetic energy, right? Which is just 1/2 M1 V final squared plus 1/2 M2 V final squared, right? Or it's just 1/2 times M1 plus M2 times V final squared. Again, they're going at the same speed at the end, so that's just 1/2 times 150 kilograms, right? It's 90, where is it? 90 plus 60 times, I think we got 4.4 meters per second. And so this comes out to like 1450 joules. So if you add these two up, KE initial is the sum of those two is 2100 joules, and KE final is less than that, right? Energy was lost in this process. In collisions, there's no reason to expect kinetic energy to be conserved. Total energy has to be conserved, but energy can be lost to heat and other things. For example, when she jumps on his back, she squishes into him. That can heat them up, their skin or something like that. When the bullet goes into the guy's bulletproof vest, it tears the fabric and tears the material in there, and energy is lost in that process. So there's no reason that kinetic energy has to be conserved, and so we shouldn't expect it to be. Total energy would have to be conserved. If you could account for the heat that's produced in these collisions and all that, and added up all those energies together, all the little ones that are hard to find, then you would be able to account for the total energy. But if you can't account for those, if you're just looking at the kinetic energy, it's easy to see that kinetic energy is not conserved. I bring this up because there are classes of collisions where kinetic energy is conserved. They're called elastic collisions. And in the kart demonstration, when I was using the magnets to allow them to repel, those collisions are pretty close to elastic. If you look at balls on a pool table, those collisions are pretty elastic. They conserve most of the kinetic energy. Collisions that are super bouncy have a decent chance of being elastic or mostly elastic. Collisions between molecules in the air are pretty elastic. But we shouldn't expect it all the time.